Hi folks, in this course in a series of grade 12 high school chemistry tutorials, we'll be introducing the concept of quantum numbers for electrons and to explain how these have been derived by the various scientists involved. However, before you continue watching this video, I implore you to look at video number 4 that dealt with the model of the atom proposed by Niels Bohr, since the knowledge of which is an essential prerequisite for the understanding of how other quantum numbers have been derived. Nevertheless, we must have a brief review of the model of the atom proposed by Niels Bohr, since it lays the foundation upon which the rest of the tutorial is established. This figure here depicts how the emission spectrum for hydrogen is produced. This structure here is a hydrogen discharge tube. A hydrogen discharge tube really is a cathode ray tube that is filled with hydrogen gas for investigation. The hydrogen discharge tube, of course, is connected to a variable voltage source. This is a knob here, and this can adjust the voltage across the two electrodes within the hydrogen discharge tube. Recall that the cathode ray tube has two electrodes. It has a cathode here and it has an anode here. And at a certain minimum voltage, electrons are peeled off the cathode and they move in that direction there towards the anode where they end up. Of course, you have hydrogen gas inside here, and inevitably these electrons that are zipping off the cathode will collide with these atoms inside here. So this is the deal. When the voltage is gradually increased across the electrodes, someone looking through this diffracting grating here sees a red photon of light being produced first. Then as the voltage keeps increasing, three other lines are observed in sequential fashion. Of course, we know as you move from left to right of the visible spectrum, the energy of the photons increase in that direction there. So as the voltage keeps increasing, then photons of increasing energy were observed. Niels Bohr will use these observations to propose his theory of the model of the atom. Niels Bohr will deduce that electrons are arranged around the nucleus of the atom in discrete quantized energy levels or shells, and that they move around the nucleus of the atom in circular orbits like the way the planets move around the sun. For each of these orbits, he ascribed a principal quantum number n. Bohr reasoned that as the voltage across the electrodes increase, the energy with which electrons are peeled off the cathode increase proportionally, causing them to bump the orbiting electrons in the hydrogen atoms to higher energy levels. When these excited electrons fall back to their original energy levels, energy was produced in the form of photons of light. The energy produced was equal to the difference in energy between the two shells. This figure here depicts the Bohr model of the atom. So this is what Bohr is saying. You have a central nucleus here, and electrons are orbiting this. They can't be found in any of these clear areas here. They can only be found in these shaded areas here that he called shells. What he's saying is that these electrons here that are being peeled off the cathode, if they encounter an orbiting electron from the hydrogen atom, they can impart enough energy to this electron here to cause it to be bumped into an orbit of higher energy, as happened in this case here. But of course, the excited electron does not like to stay there. It wants to go back to its ground state here. And in so doing, he's saying that a quantum of energy is released that was seen as a photon of light. The fact that a photon is produced means that there exists a difference in energy between these two orbitals here. When the voltage across the electrodes is made higher, he's saying that the energy with which the electrons from the cathode are peeled off keeps increasing. So if it has a higher amount of energy, not only can it bump this electron to this orbit here, but it can bump it up to an even higher orbit. And of course, this doesn't want to stay there. It will fall back and it will give off a different photon of energy. So those photons of energy enabled Bohr to formulate his theory of the atom. You have a central atom here, and electrons are going around these in circular orbits like the way the planets are orbiting the sun. All right? Of course, Bohr was awarded the Nobel Prize for his work, but there are some deficiencies in his model. The model proposed by Bohr only worked for the hydrogen atom, as it could not explain the emission spectra for atoms in more than one electron. Secondly, according to the laws of physics, any object moving around in a circle undergoes acceleration and releases energy. So if electrons are moving around the nucleus in circular motion, they do undergo acceleration, and as such they should lose energy and spiral into the nucleus, causing the atom to collapse. But this does not happen in nature. This figure here depicts the different principal quantum numbers that are ascribed to the various shells. So this K shell here is given the principal quantum number of n equals 1, L shell n equals 2, M shell n equals 3, N shell equals 4, and so on like that. These are indicating to us the different patterns in which radiations are detected in the electromagnetic spectrum by various scientists. Jacob Balmer found that only when transition takes place from n equals 2 upwards, then quanta of energy are produced in the form of photons that the eye can detect. Theodore Lyman found out that when the transition takes place from n equals 1 upwards and back, these can only be detected in the UV portion. And then Frederick Patin, he discovered that when transition takes place from n equals 3 upwards and backwards, then these are detected in the IR part of the electromagnetic spectrum. Enter French scientist Louis de Broglie. Louis de Broglie proposed his famous wave equation here. He's saying that the wavelength of any particle that's moving can be calculated using this equation here, where h is equal to Planck's constant, m is the mass of the particle, and v is the speed. He created this equation based on his reasoning that since light, which exists as waves and demonstrate particle-like properties, then all particles must also have wave-like properties. And based on his equation, massive particles will have very small wavelengths. However, small particles such as electrons will have wavelengths of significance. So if you go back to this equation now, he's saying that, look, this is how the wavelength can be calculated. So if a particle is very heavy, definitely because this is the denominator here, that is going to be very small. But if you have very tiny particles such as electron, then this wavelength becomes significant. His hypothesis created mixed reactions within the scientific community, but it nevertheless gave credence to the Bohr model of the atom. Later, his hypothesis was validated by British scientist J.P. Thomson, son of J.J. Thomson, who was able to experimentally demonstrate that electrons indeed exhibit wave-like properties. Along with American physicist Clinton Davidson, who accidentally discovered wave-like properties of the electrons, J.P. Thomson was eventually awarded the Nobel Prize in 1937. Albert Michelson. He discovered that some of the spectral lines of the hydrogen atom really existed as a number of lines. These were found, for example, when transition took place from n equals 2 to n equals 3, but not from n equals 1 to others. So what he's saying is this, that this line here really existed as two lines, not a single line. or we can put it here, this line here existed as two lines. So if we look at this line here, where there was a transition happening between n equals 2 to n equals 3 and back, that line here was really observed with two different lines. And this is indicating to us that within a shell, there can be electrons that are having more energy than others within the same shell. Later on, we'll find out that these two lines really are due to electrons being found in two types of orbitals. One is called the s orbital, that is spherical in nature, and you have these dumbbell-shaped orbitals. Okay? And because of the difference in their shapes there, obviously electrons are going to have different energy. For example, watch. An electron in this s orbital here, because it's closest to the nucleus, will have less energy than an electron in this p orbital here. To move an electron from an s orbital upwards requires more energy than moving an electron from a p orbital upwards. So when they fall back, they give a different amount of energies, and that is why you're seeing these two lines there. Arnold Sommerfeld in 1919 would ascribe secondary quantum number L to what he calls subshells. So to account for the difference in energy of the electrons within a shell, Arnold Sommerfeld introduced the concept of the secondary quantum number L. The concept of subshells that comprise a main shell was introduced. That is, each subshell was assigned a specific value of L. As will be shown later, the difference in energy of the electrons within the subshells are associated with the shape of the electron orbitals. We have not done that yet. I have alluded to that already. The difference in energy is due to the difference in the shape of these orbitals there in which the electrons are present. For the first shell, where n is equal to 1, there is no subshell, and L is given the value of 0. So the K shell that has only 2 electrons would only have one orbital with no subshell, and it is given an L value of 0. For the second shell now, there are 2 subshells, and L is given values of 0 or 1. Later you'll find that when n is equal to 0, it corresponds to the S subshell, and when L is equal to 1, it corresponds to the P subshell. For the third shell, where n is equal to 3, there are 3 subshells. Note that the number of subshells correspond to the principal quantum number n. When n is equal to 1, there is no subshell. When n is equal to 2, there are 2 subshells. When n is equal to 3, there are 3 subshells. And L can be given values of 0, 1, or 2. Always when L is 0, it reverts to the S orbitals. When L is equal to 1, you're talking about P orbitals. And then now later on you find there's a third set of subshells that's called D orbitals, and these will give L quantum number of 2. Magnetic quantum number ML. In 1896, Peter Zeeman, Dutch scientist, observed that if a gas discharge tube was subjected to a strong magnetic field, some single lines could further be split into new lines. This effect is called the Zeeman's effect. For example, one of the split lines initially present during electron transition n equals 2 to n equals 3 and back was split into 3 lines. So what this is telling us is this. You see these 2 lines here that came from this one line? It is discovered that one of these lines here was further split into 3 different lines. When the gas discharge tube was subjected to a strong external magnetic field. This was the original line that was observed, but then we discovered that this line here was split in 2. We said that this one here was associated with the s orbital in the second shell, and this one here was associated with the p orbitals. Now, this one here was split into 3 here. Okay? So for us to understand how this happened, we need to understand what happens when a current carrying conductor is subjected to a strong magnetic field. For example, if I have a wire here, the current is moving in that direction. This wire here establishes its own magnetic field in the form of concentric circles, and the magnetic field is in that direction as indicated by these arrows here. If the current in another conductor is moving in this direction, then it establishes a magnetic field around it in the form of concentric circles also, and this is the direction in which the magnetic field is. If I place this conductor inside this magnetic field here, and I take this other one here and also put it inside this magnetic field that's produced by these two strong biomagnets here, and I have a third conductor in which the current is flowing in this direction here. So the current in this one is flowing perpendicular to this magnetic field here, and the same thing is happening with this conductor here. The current is flowing perpendicular to this magnetic field, but the current in this conductor here is parallel to the magnetic field. What happens is this: because this is having a magnetic field of its own, and we put that inside an external magnetic field, there is a resultant magnetic field that causes this conductor to be pushed in that direction here, and this conductor here will be pushed in this direction. And this is the principle of which the electric motor is built. This one is not affected. The fact that a single main line as subshell was split into 3 lines with different energy indicates that within the subshell there are 3 different angular orientations of electron spin, each having its own associated magnetism. So when these react with the external magnetic field, they acquire different amounts of energy as indicated by the 3 different lines. Otherwise, in the absence of an external magnetic field, these will have the same shape, energy, but different spatial orientation. Arnold Sommerfeld and Peter Debye in 1916 used a third quantum number ml to explain the Zeeman effect. The following table gives a summary for some quantum numbers. So here you're having the principal quantum numbers, and n is equal to 1. Of course, in that shell here you're having only 2 electrons, which is the s electron, and all these s electrons will have a secondary quantum number of 0. And because they don't make an angle, they have a magnetic quantum number of 0. So 2 things to know about s orbitals. You'll do the shapes later on. I'm just preempting that a little bit. All s orbitals will have 0 secondary quantum number and 0 magnetic quantum numbers. Okay? The second principal quantum number n equals 2. Of course, you have 8 electrons. So 2 of these will be in the s orbital, and 6 of them will be in these 3 p orbitals here. All p orbitals will have a secondary quantum number L equals 1. But now look, because you're having 3 different orientations of these orbitals, they have 3 different magnetic quantum number. You have -1, 0, and +1. Just like how you have those 3 conductors with current flowing in 3 different directions, it is subjected to 3 different motions, right? Because of a different direction in which the current is moving. Just like that now, because the electrons in these are moving, okay, in 3 different orientations, they're going to have magnetic quantum numbers of -1, 0, and +1. I do not know which one corresponds to which, but if you assume that this one is 0 here, okay, you can probably say this one is -1 and that is a +1. Now, for the third shell, you have a principal quantum number n equals 3, and of course you have 18 electrons in this shell, and you're having 3 different subshells. You're having an s subshell that will have 2 electrons, and of course we said that s subshells will have secondary quantum number of 0, magnetic quantum number of 0. So you have 2 electrons in these, and in these 3 p orbitals here you're going to have 2, 4, 6 electrons, okay, And of course, the p will have a secondary quantum number L of 1. They're going to have the same type of magnetic quantum number here, 0, -1, +1. But look what happens with the orbitals. In the first shell, this s orbital is small. In the second shell, it gets bigger here. In the third shell, the s orbital is bigger, and the p orbitals are also bigger. You're going to have these same magnetic quantum numbers here for these. These will hold 8 electrons out of these 18. So you have 10 remaining electrons now. Here comes in a different type of orbitals that we learn about later on that are called d orbitals. So look what happens. For n equals 3, you're having s orbitals having 0 secondary quantum number, 0 magnetic quantum number. P orbitals are having 1, L equals 1, ML equals -1, 0, and +1. But now because you have 5 different d orbitals that are oriented along different axes here, later on we talk about these. D orbitals are 4 lobe orbitals, 4 of them are 4 lower orbitals, and this one is like a dumbbell shape passing through this donut-like structure here, okay? And because they're oriented along these different axes here, they're described as such. This is dyz, dxz, dz square, dx square minus y square, and this is dxy. So this is how quantum numbers have been derived so far. You have 3 of them. But now there's a 4th quantum number that is called the spin quantum number. Wolfgang Pauli suggested that the 2 electrons present in an orbital spin in opposite direction. One spins in a clockwise direction and the other in an anti-clockwise direction. And because that, each electron creates its own magnetism. So if an electron is spinning like this in a clockwise direction, then this one end of the atom here will behave like a north pole, and this one will be like a south pole. And the other one here will have a different kind of magnetic polarity, okay, because of the different direction of the electron spin. This one we'll call ms equal to positive half and a negative half. So that's easy to deduce. You have 2 electrons, just call one negative half and a positive half, all right? What kind of quantum numbers will you give this one? Definitely, this is a dz square orbital. It'll have a principal quantum number of n equals 3. L is going to be equal to 2, y2. You have to distinguish from p orbitals is equal to 1. If you assume this is parallel to the magnetic field, we can say that ML is equal to 0. And definitely you're going to have these 2 here. Okay. You have 4 different types of quantum numbers to describe electrons in the different orbitals, okay? The table here gives a summary of some of them. When n is equal to 1, you only have s electrons. If I give you these quantum numbers, how would you know what type of electron am I talking about? If I say n equals 1, L is 0, ML is 0, I'm talking about an s electron. If I say to you n equals 2, L equals 1, and I say ML is equal to -1, I'm talking to you about a p electron in the second shell. If I say to you n equals 3, L equals 0, ML is 0, I'm talking about an s electron there. If I say to you n equals 3, L equals 1, and ML is equal to 0, I am talking about this. If this is parallel to the magnetic field, I am talking about this orbital here. If I say to you n equals 3, L equals 2, I'm talking about some one of these 5d orbitals here. And I say, let's say this one corresponds to that, ML is equal to this one here. I'm talking about this orbital here. And of course, the 2 electrons, one is going to be ms is equal to positive half and negative half. I hope that was useful to you. All right, bye-bye. I hope that was beneficial to you. Our next tutorial deals with atomic orbitals. Please don't forget to subscribe.